from My name is Lu Bing, and today I would like to share about the gVisor container on ARM. So this is my agenda. We will talk about what is gVisor, and then the background of gVisor on ARM, and then the architecture, the details. So first, what is gVisor? For containers, there is a lot of concepts like secure container. So our team is hoping to introduce more and more solutions with the secure containers on our ARM. So first, let's talk about the concept of the secure container, and then we will introduce the gVisor and its architecture, and then I will talk about the technical implementation details of gVisor in ARM, and then what we have done, what we will do. gVisor, first, it is a solution for secure container or for trusted computing. So far, it is compatible to OCI, so that means it can run in Docker. It can be called by the different solutions like CAI. And the most important modules for gVisor, the first is the user space kernel, which is called Sentry module. So it is from Go, and then OCI compatible. So that is why it can independent working as a container runtime. And then isolation platform. This is very important for the different platforms, the PowerPC platform or the ARM platforms. The portability work is the isolation platform. So far, there are ptrace and KVM for the isolation. And for ARM, now we began to implement the isolation platform implementation in the community. So this is a simple architecture of gVisor. For the gVisor architecture, just remember the number 3. So first is the Sentry and the user space kernel, and second is the platform, and the third is the gVisor, which is mainly for I/O operations. So this page is about the ptrace platform architecture. So the left app is the apps of the container, and the ptrace is using sysemu feature. So in the ARM environment, sysemu is kind of imported to the kernel. And then for the ptrace platform, the ptrace kernel is used for the syscore. So before talking about for ptrace, for user kernel and host kernel space interaction, one is syscore, while the other is interception. So this page is mainly using sysemu to intercept syscalls and then stop the progress and then to allow the context to be modified. The context here is about x0 to x31. And at the code level, if we are doing some porting work, the modification of code is to intercept syscalls or segmentation for. And for ptrace platform, the main work is some Go based language. It is related to the change of the commands, and except that it is very similar to the X8 platform. And another platform is KVM Platform. It is totally different, including the MU, the page table, and the virtualization. So for KVM Platform, most of the porting work are different. So next I will talk about this. So this is the KVM Platform, the architecture here. The top left corner is the apps, and then the right is the user space kernel and the IO operations. So for KVM platform, for the ARM platform, a core concept is we need to give some vCPU for your program or your applications. And then when the apps is entering the kernel space to have the EL1 mode. So that means for the ARM platform, it is providing 16 exceptions, and for the KVM platform, it is capable of building a vCPU and guaranteeing that the 16 exceptions will be seized and will be modified. So we can have a look at the left-hand introduction. For user space kernel, first it has provided a sentry module in guest kernel, and then in the guest kernel, it will have the vCPU configuration, the list of the abnormalities, and then how to exit from the virtual machine. So that are all very different from the X6 platform. And for KVM platform, it has provided a Type 2 hypervisor. It is different from Kata. And for Kata, for the Type 2 hypervisors, they will simulate a guest-led kernel. But for the KVM platform, the Type 2 hypervisor is to provide the vCPU and allow the apps to enter into the EL1 mode via syscall. And for the syscall interception, we need to know how to intercept. And for PX6 platform, if to visit a illegal instruction, it will not trigger illegal. But for ARM platform, we will trigger a signal illegal. And also for ARM platform, when exiting from the virtual machines, it is difficult from the X8 mechanism. For ARM, we are different. And about the gVisor storage. For the gVisor storage, there are the following aspects. First, it's essentially the user space kernel, and second is gVisor. So for this, gVisor played a role of proxy, and currently it is via NAMP connection, but we know that actually the NAMP connection has been replaced by NVDIM. For NAMPS, the performance is very low. So we have done some tests. For 1 second, it is about 100 megabytes. For the gVisor networking, it is also very powerful. So the core thinking is to intercept the syscalls. So that means how to deal with the network stack. So gVisor has provided a user space IP stack. There are a lot of user space stacks. For DPDK, they are using another kind of user space IP stack. For Google, they have provided some like user space IP stack in Go language. So you can go to that link if you have interest. And for the gVisor networking, it has realized its own IP stack, which is called NetStack. So for gVisors, what it can realize is VAS device. So it can support the overlay and direct routing, and also it can realize the network pass-through mode. That means if to deploy gVisor into Kubernetes, can use this kind of mode. And for the ptrace platform, how to run a hello world on ARM. So we can see that gVisor, in terms of compilation, we will use select to differentiate the two different platforms, while the repos and the process is very similar. So if you have interest, you can have a look at this code to see how it is track the anomalies, and then realize that the user space. So it is very easy to debug the central user space kernel in the ptrace platform. So this is a kind of initial process. So we can see that the red letters to run a hello world. What is very important is we need to have a look at the exec, and the other things like checkpoints are we actually haven't realized that. And for gVisor checkpoint, maybe it is via CRU. So far, I haven't been involved in that kind of stuff. So this is the hello world code level demo. So you can see that all the .a documents has been enabled, including architecture, file memory, interrupt. So later, I will have a demo to you on how it is running on the ARM platform. So all the codes has been delivered to the GitHub.
KVM platform is relatively more complex. For our side, gVisor's principles are known to you. It is intercept the system call and simulate those system calls so that we can ensure the container can have minimum execution on the kernel space. So a lot of things are done on ARM 1.0. For KVM platform is the second inception platform of gVisor. Its major function is to provide a very good performance of the isolation. So it can also use the signal to provide a subprocess. So that method has relatively less performance with PH platform. Normally it's used for debugging, and for Sentry, there's a lot of difference from ARM. Of course, the difference is not as many as isolation form. There are still some gap on ARM platform and x86 platform about the number of the system calls. Sometimes the names of the system calls are different. Right now, in Sentry, for some safe system calls, most of them are consistent with ARM, but there will be single-digit inconsistency. So on isolation platform, after we have done that, we're going to bring those inconsistent system calls on x86 to the ARMs. We're going to eliminate those. Now let's look at KVM platform. If we're going to achieve KVM platform, the first thing we need to focus on gVisor's memory management. On ARM platform, our memory management and tables are different. For x86, and the page table should be 46 or 47, and it's also using superpage, so you can have 1 gigabyte or 2 megabyte for management of page tables. So it's different from ARM. For ARM's page tables, there are two formats. One is identity mapping, the other is section mapping. Identity mapping can configure 4K, 16K, 64K. So we're also using 4 levels. This is consistent with x86. When we are configuring 4K and 4 levels, on ARM's KVM platform, it can start from the latest kernel to configure the physical address. For the previous versions, the physical address is fixed. PA is 48. So we have achieved that for 6K and is 4K. And for gVisor page table folders, you can find these. If we're going to configure that to 4K, the levels would be 3. The default for the current setting is PA is 48, VA is 48, and 4 levels. Because gVisor's core function is to provide reliable computing, normally it will be deployed in the serverless environment. We know that for serverless environment, there are 2 indicators that are important. One is put up time, the other is container density. For x86, it configures super page so that you can quickly manage the memory with page tables. It will be very fast, so it's essential for put up time. So our next step will be putting section mapping. We can also use 1G for that. The next one is set memory region. The function of set memory region is to map HVA and IPA. IPA is the so-called guest physical address. Memory on gVisor's KVM Platform's memory management, these two are closely related. It involves GVA and IVA's mapping. The second step is IPA and HVA's mapping. That determines these two mapping relationship will be fixed during initialization. And then for the context modification in the container, how do we identify the correct HVA and GPA? It would be based on the memory management, and these two steps are very important. If you are interested, you can try to read the code. How does it achieve mapping from GVA to IPA and IPA to HVA? This one is about the prepare mechanism. If you know something about that, on gVisor there are three modules which are very important. One is procure, the pure. The second one is running pay table. So we have shown you about the implementation of the page table on ARM platform. So this is about prepare platform. The first one is about signal action. The biggest problem, we know that in Go language, it develops very rapidly, but for virtualization, it has a lot of things missing, so it cannot be compared with C language or Rust language. So there are many things you need to pay attention to. For example, for the first one, for the signal action, in the Go, you also need to operate the storage. You also need to follow the instruction. There are many instructions that are not implemented, so you need to use the word. There are also some problems. So for ARM's Go compiling, it used as tools to store the Go ID, and there are two designs. One is Go routing design, and the other is system design. For the KVM system, if you are going to call Go functions, and which stack do you need to use? This is something you have to pay attention to. If you have used C for compiling, and you can use stacking, but for Go it doesn't work that way. The second one is about KVM Type 2 hypervisor. I have said that it's not running the whole Linux on gVisor. So it can ensure that you can enter the kernel mode through system call, and KVM platform will capture the list and also the context. The third one is exit from the VM. On x86, one technical details is that in the hot exit of KVM, it has a mechanism. In ARM platform, we don't have the mechanism. Now we're using MMR exit mechanism. In virtualization, we have a method to exit ARM-SID. Our design is that for ARM's virtualization, for the memory management page, if in step 1, if MNA can find the address, if we can identify the mapping relationship, but for the second step, if we can't find IPA or HVA, virtualization would have an VM exit, so we need to design that separately. Right now for ARM, on MR exit, so we need to fill the mixing context and then check the abnormal items list. The first one is enabled vector table. So it's in the running folder of KVM. There are also something we need to pay attention to. For example, for abnormal items list, and it's aligned by 11 bits. And for the 16 abnormal items, it will be aligned by 7 digits. And sometimes we need to use the test codes for the compilation. Currently, we are dedicated to build our interception platform, and then we are supporting the system calls. For example, we have a common system call which is called PAL, which is not available on ARM. But we have similar system call. That's why we can use a select to switch different logic analysis. The next chart is about running Hello World demo. We can see the operating environment is ARX. For the next step, quite a lot. First, we want to push the codes on our hand to upstream, and also in the kernel, we also have some patches that we need to submit for the kernel. For the next step, we want to achieve the system call on the user space. We also need to pay attention to performance. For example, like 9PFS, there's room for improvement of performance.
So there's a demo. So first, this is the ARM server. So from this, we can see that for the gVisor runtime name is runsc. We can have a run. So for Hello World, it is working very well on ARM platform. So we'll now look at the code. Okay, so with that, I come to the end of my speech. Any questions? So my question is for the simple syscalls, how is the performance? Yeah, actually in our plan, we got it. We include that in our plan. Because as you may have done, after you have done most of the work for the code itself, you need to standardize the codes. For example, for the memory management, we didn't adopt the 1G. We will switch to 1G. So after finishing the related work, I think that we will start to do that. Okay, my second question is from your perspective, how active is gVisor in the community, and what is the development trend of the users? Yeah, it is very active in the community, and I think for the trusted computing or for secure container, it can be regarded as another Kubernetes. And for gVisor, as I have mentioned, it's a secure container solution. So that means when our users are thinking about secure container, you need to know whether the code is from third party, maintained by third party. So if that is the case, you need to have the secure container, because for the security white paper, it is very clear that you need to do that. And also, as I have mentioned, the time of gVisor is the same with runsc. So that means it is very suitable to put into the serverless environment. When customers is calling the PI, it is very easy to call it, and the container density is also good. I do not quite understand one of the ptrace, why we need to have a ptrace sysemu. The function is, for example, you can have a test.c to test the ptrace. The ptrace, when you have got a application call, it can stop the kernel or it can skip the syscall. Yeah, I know that. So my point is, why do you have come up with that as an extra? Because for ARM, we do not have this function. So the CCMU is to be included soon. So that means if during the interception process you do not need to deal with the mirrors and then to invoke the context, you can resort to the functions to change the context. So that means I can quickly get the context, and then ptrace the performance, how it can be worse than that of KVM. One, there's because it has no zero copy. That is the switch between the different contexts, because all the copy actually has already been finished. And another thing is that it is adopting signals for communications. You have mentioned that You need to use signals to inform the neighboring layers, and then to use that or get signal or commands. So my point is that actually for ARM we are using it like this. Think that what you are using is ptrace but not using ptrace CMU. And also for the ARM system, it is not only this MU which can change the context. You can refer to that actually there are three ways. And for X8, it is using CMU. And for ARM, there is another Android kernel. It is consisting of two commands. So the first command is kind of to slow it, and then to skip it. Then the next step is so-called modification of the context. It is the nullity patch. But to be consistent with XA, we are using the CMU. So another specific question is about the gVisor. For gVisor, the timing. When, for example, users has invoked a syscall and it is still running EL1. Yeah, because it is a vCPU. They are running in the. So for the ELE the list open. So for that we are different in ARM, and for ARM there are one is the user space, the other is the kernel space. So you know that it is different from the platform. But when we are designing, we will also take into consideration the difference. Thank you. Thank you.